Relativity! Part 1. Special Relativity. Relativity as a concept means that there's no absolute standard against which to measure things. That is, everything is relative. This is readily apparent in semantics. You can't just call something big. It's big in comparison to something else. For example, a skyscraper may be big compared to a person, but it's insignificant compared to the size of the entire Earth, while the Earth, in turn, is insignificant when compared to the Sun. Now, while relativity is nowadays attributed to Albert Einstein, the first theory of relativity was actually postulated by Galileo. His idea was that the laws of physics applied no matter where you were, no matter what you were doing. So gravity and the laws of motion and all that would apply whether you were on Earth, or in the center of the Sun, or flying through the empty vacuum of space. But the odd thing about Galileo's relativity is that he believed there was an absolute frame of reference, as if the universe were a great big three-dimensional piece of graph paper and every single physical interaction could be mapped out relative to this universal grid. Galileo also came up with the idea of the inertial reference frame. Inertia is the state of neither speeding up nor slowing down, as well as the resistance to speeding up and slowing down. So if you're not moving at all, you're in an inertial reference frame. If you're moving at a constant speed, you're in an inertial reference frame. If you're accelerating, then you're not in an inertial reference frame. Galileo postulated that in an inertial reference frame, you won't be able to tell whether you're moving or not. Think about when you travel in a car. If you're maintaining a constant speed, close your eyes. Don't do this if you're the one driving, obviously. With closed eyes, can you tell how fast you're going? You shouldn't be able to. 40 miles per hour should feel exactly the same as 80 miles per hour or any other speed. But if you were to slam on the brakes or hit the gas, you'd be able to sense not only that you are accelerating or decelerating, but how much you are doing so. For another experiment, in the car going at a constant speed, throw something in the air. It should go straight up and straight back down. But if you throw it into the air as you slam on the brakes, it should fly forward. You, being wisely attached to the car by a seatbelt, remain in one place, but the thing thrown in the air, having no force acting upon it to slow it down, keeps going at the same speed and it flies forward. So there's a fundamental difference between inertial reference frames and non-inertial reference frames. Now enter Einstein. Einstein came up with two theories of relativity. The special theory deals mainly with inertial reference frames, while the general theory also incorporates non-inertial frames. Let's start with special relativity. It's a little bit easier. Key to special relativity is the idea of the vector. A vector is a measurement of a quantity that has a direction. For example, distance and velocity are vectors. When you say, London is 400 miles east of here, you're giving a quantity, 400 miles, as well as a direction, east. If you just say 400 miles from here, then you're given relatively little information. Same with velocities. If you're going 60 miles per hour, you're going that fast in a certain direction. If a quantity does not have a direction, it is called a scalar. Mass is a scalar. When something is 50 kilograms, it's not in a particular direction, it's just 50 kilograms. Now, a vector is usually made up of components, smaller vectors that point in specified basic directions. For example, if you say Beijing is 500 miles southwest of here, you're saying that it's a certain distance to the west and a certain distance to the south. These two distances add up to make a vector in the southwest direction. Now, in physics, we don't usually say south and west and east because those directions really only have meaning on Earth. We instead go with the three axes of a Cartesian graph, x, y, and z. So if we say that Pluto is 5 billion kilometers from here, we mean that it's a certain distance in the x direction, a certain distance in the y direction, and a certain distance in the z direction. Now, if we kept the same distance away, but merely changed the direction, we would have varying quantities in each direction. If Pluto were exactly on our z-axis, then it would be 5 billion kilometers away in the z direction, but no distance at all away in the x and y directions. And as Pluto moved away from the z-axis while keeping the same distance, then the amount of distance in the z direction would be smaller, while the amounts in the x and y directions would get bigger, as long as adding all three always added up to 5 billion kilometers. This can also be done with speeds. If a rocket ship is heading away from Earth at 500 meters per second along the z-axis, then it would not be heading away from Earth at all in the x or y directions. But if it kept the speed of 500 meters per second and just changed direction, then the speed in the z-axis would decrease, while the speed in the x and y-axis would increase, as long as all three added up to 500 meters per second. This is summed up mathematically with the Pythagorean theorem. Calling our vector v, we get v squared equals x squared plus y squared plus z squared. Now, Einstein's special theory of relativity says mainly two things. The first is that time can be considered a fourth dimension alongside the x, y, and z axes of space, and is usually labeled t. So we get the four axes of unified spacetime, x, y, z, and t. This gives a new Pythagorean equation of v squared equals x squared plus y squared plus z squared plus t squared. Einstein then said that one speed through spacetime is constant. It is always the speed of light, 300 million meters per second. Normally we don't travel through space at 300 million meters per second, so most of our intrinsic speed is diverted into time. The implication of this is that the faster you move in space, the slower you move through time. If we were to travel at a significant portion of the speed of light, say over 50% or at least 150 million meters per second, we would start to notice time around us slowing down. We would perceive time to be going at the same rate for us, but if we, in our spaceship going 150 million meters per second, looked back at Earth, we would see Earth going through time at a much faster rate. Everyone would flit around like hummingbirds. You can think of traveling at half the speed of light as a way to press the fast-forward button for the rest of the universe. Conversely, someone back on Earth watching our spaceship would see that we were moving through time much slower, as if we had suddenly been put into slow motion. This disparity between two inertial reference frames only happens when you can obviously tell which object is the one moving at half the speed of light. The Earth itself, as well as the Sun and all the other planets, are all moving at very high speeds. But since they all move at those speeds together, we don't notice any changes in time. Time only speeds up and slows down like that for relative motion. If you're going a significant portion of the speed of light relative to something else. If you were going half the speed of light in empty space with nothing around you, you wouldn't be able to tell if you were even going that fast. This is where Einstein refutes Galileo. There is no absolute frame of reference. There's no grid of the universe on which to measure speeds and distances. Things can only be measured relative to other things. There's one final implication to special relativity. You should be familiar with the formula E equals mc squared. What you haven't been told is that that formula is actually wrong. The real formula is E squared equals m squared c to the fourth plus p squared c squared. E is the energy of an object, m is its mass, and c is the speed of light, 300 million meters per second. P is the momentum of an object. When something isn't moving, the only thing that matters in how much energy it has is its mass. Its rest mass, to be precise. Because as an object starts to speed up, it starts gaining mass. At the kinds of speeds we're used to on Earth, like 60 miles per hour, we never go fast enough to feel the effects of this. But when you start going a significant portion of the speed of light, your mass increases drastically. And the more mass you have, the harder it is to speed up. Mass will increase at such a rate that anything that has mass to begin with, even an electron, which weighs less than an octillionth of a gram, will have an infinite mass at the speed of light. Of course, it's impossible to have infinite mass, so the practical result of this is that it's impossible to go at the speed of light, at least relative to anything else in the universe. The only reason light can go at the speed of light is because it has no mass. The energy it has derives completely from its momentum. Besides being massless, light also does not experience time at all, since all of its space-time vector is taken up in space. So if you found a way to strap a clock to a photon, and then found a way to view said clock, it would appear that time had stopped on the photon. And since light is not allowed to have mass, and is also not allowed to experience time, it has to be traveling at the speed of light relative to everything. Think about this for a second. Imagine a train in the middle of a desert coming up to a train station. If it's coming up at 100 miles per hour, the people at the station will think it's coming in at 100 miles per hour. But if you're in a car driving alongside the train, going at 90 miles an hour, then the train would seem to be going only 10 miles an hour relative to you. Now, if it were light instead of a train, then the train station and the car would not see different things. They would bizarrely see the same thing. If you're in a space station, and you see a photon going at the speed of light, and a spaceship going at 90% the speed of light, then it would seem like the photon were traveling just a little bit faster than the spaceship. But if you were in the spaceship, then you would see the space station whip by at 90% the speed of light, while the photon rocketed past you at the full speed of light in the other direction. This idea that how you're observing something can actually change the physical universe helped lead to the weirdness of quantum mechanics. To be continued in Part 2.